A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
I was looking at some system architecture diagrams this morning, and it hit me that we are living through a period where the distinction between a high-growth tech startup's infrastructure and a modern military's command structure is basically evaporating. It is all just data engineering now, just with much higher stakes and more kinetic outcomes. Today's prompt from Daniel is about this exact intersection, specifically how sensor fusion and military architectures like joint all-domain, command and control mirror the civilian data challenges he sees in things like Grafana dashboards and Prometheus queries.
It is a brilliant observation, Korn. I am Herman Poppleberry, and I have been deep in the weeds on this because of what we just saw with Operation Epic Fury a few days ago. If you look at the reports coming out of the strikes on March 13, 2026, the real story wasn't the airframes or the munitions. It was the software pipeline. We are seeing the culmination of a decade-long shift from military hardware being the primary asset to the data pipeline being the primary weapon. People see a drone and think robot, but they should be looking at the metadata stream behind it.
You are talking about the Maven smart system, right? I saw the register reporting that the Department of Defense basically compressed what used to be 8 or 9 separate targeting platforms into a single integrated pipeline for that operation. That is a massive consolidation. If I am a developer and I hear that we went from 9 disparate legacy systems to one unified stack, my first thought is usually, okay, who had to write the middleware that survived that transition? And more importantly, how did they handle the technical debt of 40 years of Cold War-era sensor logic?
That is exactly the right question. For years, the military suffered from what architects call the point-to-point integration anti-pattern. If you have 5 different sensor systems, let's say a radar array, a satellite feed, a drone's infrared camera, and some signals intelligence, and you want them all to talk to 3 different shooter platforms, you end up building custom integrations for every single connection. The math on that is brutal, Daniel. It is n times n minus 1 divided by 2. As you add more sensors, the complexity scales quadratically. You end up in integration hell where nobody has a clear picture because the data is trapped in these custom-coded silos.
It is the same thing Daniel mentioned with Grafana. If you are pulling networking arrays from Prometheus and trying to overlay them with lob data from a different database, and neither one shares a common schema or time sync, you are just staring at 2 different lies on the same screen. You have to write these incredibly complex queries just to make the x-axis match. In a military context, if your satellite says the target is at coordinate A, and your drone says it is at coordinate B, because their clocks are off by 200 milliseconds, you can't hit the target. You are effectively blind, despite having billions of dollars of sensors.
The military equivalent of that standardized dashboard is what they call the Common Operational Picture, or COP. But for decades, the COP was a lie. It was manually updated by intelligence officers who were literally looking at one screen, typing data into another, and then calling a third person on a radio. What Maven did, and why the Pentagon just raised the contract ceiling to $1.3 billion through 2029, is that it treated this as a classic ETL and streaming pipeline problem. Ingest, transform, load. They moved away from AI as a black box, and toward AI as a data normalization layer.
I want to dig into that architecture because Daniel specifically asked about the military equivalent of something like Apache Kafka. In the civilian world, Kafka is the message bus. It is the nervous system that lets different services subscribe to data streams without needing to know who produced them. Is the Department of Defense actually running a pub-sub model now? Or is that just a metaphor we are using to make it make sense?
Oh, it is very real. In some cases, they are literally using Kafka. There is a project called the Smart Soldier where they have been testing forward deployed hardware. We are talking about Raspberry Pis and small form factor ruggedized computers running Kafka clusters at the tactical edge. Imagine a soldier in a high intensity environment. Their wearables, their drone feeds, and their biosensors are all producers on a local Kafka cluster. That cluster then mirrors the data upstream to a mobile command post, which acts as a higher level broker, which then syncs with a regional headquarters. It is a tiered, distributed message bus architecture.
That is wild. So instead of a radio call saying, "My heart rate is up and I see a tank," the system is just emitting events. The command post doesn't have to ask for the data. It is already subscribed to the soldier's event stream. It is the difference between a pull-based legacy system and a push-based reactive system.
Precisely. That is the shift from request response to event-driven architecture. In the old world, a commander had to ask for an update. That is high latency and high cognitive load. In the JADC2 world, that is Joint All-Domain, Command and Control, the goal is for the data to find the user. If a sensor in the Pacific detects a specific radar signature, that event is published to the bus. Every system that needs that data, whether it is an Aegis destroyer or an F-35 or a satellite, sees that event in near real time because they are subscribers to that specific topic. They don't need to know the sensor exists, they just need to know the radar detection topic has a new message.
But how do they handle the schema problem? This is what Daniel was getting at with his Grafana queries. If the Air Force's radar sends data in one format, and the Navy's sonar sends it in another, you can't just pipe them into the same Kafka topic and expect it to work. You need some kind of normalization layer, or your common operational picture just becomes a common operational mess.
This is where Maven's three-layer architecture comes in, and it maps perfectly to what Daniel is asking. The first layer is ingestion. It handles the messy work of taking proprietary, often legacy data formats and normalizing them into a common schema. They use a lot of machine learning here just for the data cleaning part, identifying what is a ship, what is a plane, what is noise. It is basically a massive automated data wrangling step.
So layer 1 is the ETL. What is layer 2?
Layer 2 is the logical analysis. That is where the sensor fusion actually happens. It takes the normalized data from multiple sources and creates a single synthetic track. It says, I have 5 different sensors telling me there is an object here, based on their confidence intervals and the physics of the environment. This is where that object actually is. It is resolving the 2 lies on one screen problem by calculating the most probable truth.
And the third layer?
The third layer is the actionable output. That is the presentation layer Daniel mentioned. It is the dashboard that tells the commander, here is the target, here is the recommended weapon system, and here is the estimated collateral damage. It is taking a petabyte of raw sensor data and distilling it down to a single yes or no decision for a human.
The efficiency gain there is almost hard to believe. You mentioned earlier that Maven reduced the targeting staff from about 2,000 people down to 20 for the same operational output. That is a 100-to-1 reduction. If you told a CEO they could reduce their operations department by 99% by fixing their data pipeline, they would think you were selling snake oil. But in the military, that operations department was just thousands of people manually moving data between incompatible systems.
It sounds like an exaggeration until you realize how much of military work used to be swivel chair integration. You had an intelligence officer whose entire job was to look at a screen, write down a coordinate, and tell it to someone else who would type it into a different screen. That is a human acting as a high latency, low bandwidth, error-prone data cable. When you replace that with an automated pipeline, the speed of the kill chain moves from hours or minutes down to seconds. In Operation Epic Fury, they were reportedly identifying and striking mobile targets in a time frame that would have been physically impossible even 2 years ago.
It makes me think about the kill chain as a high-stakes CI/CD pipeline. In software, you have code commit, build, test, and deploy. In a strike mission, you have find, fix, track, target, engage, and assess the F2T2 EA process. It is the same flow. If your test phase, which in this case is target verification, takes 3 hours because the data is stuck in a silo, the deploy phase is useless because the target is moved. You need continuous integration of sensor data, to have continuous deployment of effects.
That is a perfect analogy, Corn. And just like in CI/CD, where you want to catch bugs as early as possible, in JADC2, you want to push the inference to the edge. You don't want to send raw high-definition video from a drone back to a central cloud in Virginia just to figure out if there is a truck in the frame. That is a waste of bandwidth and adds too much latency. You want the drone to run the inference locally, the military equivalent of a Lambda function or an edge worker, and then just send the metadata, truck detected at these coordinates with 98% confidence.
Which brings up the challenge of what they call comms denied environments. If I am a civilian dev and my internet goes out, my app stops working. If a soldier's link to the satellite is jammed by electronic warfare, their data pipeline is severed. How does a distributed Kafka-style architecture handle a total network partition?
This is where the military is actually ahead of a lot of civilian enterprise tech. They use a concept called graceful degradation. The edge nodes are designed to be autonomous. If the soldier's Raspberry Pi loses the connection to the command post, it continues to function as a local broker. It collects all the telemetry and sensor data from the immediate vicinity. The moment the link is reestablished, it performs a state sync or a delta update with the rest of the network. It is very similar to how offline first mobile apps work, but it has to be much more robust because the packet loss isn't just a bad cell signal, it is active jamming from a peer adversary.
We talked about this a bit in episode 624, where we looked at the Palantir and Anthropic collaboration. It seems like the reasoning part of the AI is being used now to solve the schema problem Daniel mentioned. Instead of a human writing a complex query to join two tables, you have a large language model or a transformer-based system that understands the context of the data and joins it on the fly. But there is a massive hurdle here that we haven't touched on: classification.
The hard schema problem. In a civilian setting, you can usually just get permission to access a database if you need it for a dashboard. In the military, crossing those classification boundaries requires cross-domain solutions, which are basically hardware-enforced one-way data valves. In the NATO postmortem from early 2026, they found that the biggest bottleneck wasn't a lack of data, but the fact that 31 member nations were using incompatible databases and classification levels. You might have the data you need to stop a threat, but if that data is marked secret and your targeting system is on an unclassified network, the schema isn't just a technical barrier, it is a legal and security wall.
And those valves are the ultimate latency killers. If you have to pass every data packet through a manual security review, your sensor fusion is dead on arrival.
The move now is toward data tagging at the atomic level. Instead of the whole database being secret, every individual row, or even every cell, has metadata that defines who can see it. This allows the pipeline to filter data in real time, so the commander sees exactly what they are cleared to see, while the underlying fusion engine uses the full high-fidelity stream to calculate the coordinates. It is like having a row-level security policy in a Postgres database, but enforced across an entire theater of war.
It is interesting to see how this is being split across the different service branches. You have got the Army doing Project Convergence, the Navy with Project Overmatch, and the Air Force with the Advanced Battle Management System. They all sound like different names for the same thing: building a message bus that works across domains.
They are essentially different implementations of the JADC2 vision. The Air Force's ABMS is probably the most cloud-native in its thinking. They are looking at the air domain as a giant mesh network where every plane is a node and a router. The Army's Project Convergence is more focused on the tactical edge and the smart soldier concepts we discussed. But the goal is the same: to move from a command and control model, which is hierarchical and slow, to a compute and control model, which is distributed and fast.
I wonder about the adversarial side of this. If your entire military strategy is now built on these data pipelines, the schema becomes the attack surface. If I can inject poison data into your Kafka bus, say, a fake sensor reading that looks like a valid event but contains a malicious payload or just confuses the fusion logic, I can paralyze the whole system without firing a shot.
That is the new frontier of electronic warfare. It is not just about jamming the signal anymore, it is about synthesizing the signal. If you can make the enemy sensor fusion engine believe there are 1,000 targets when there are none, or hide a real target in a sea of validated noise, you have won the data war. This is why zero-trust architecture is becoming a military requirement. You don't trust a sensor just because it is on your network. You verify the cryptographic signature of every single data packet. Every event on the bus has to be authenticated. We are moving toward a world where every drone and every soldier has a unique cryptographic identity, and every event they publish is signed and verified in milliseconds.
It is funny how we have gone from talking about Grafana dashboards to cryptographic packet authentication in 20 minutes, but it is all the same thread. Daniel's intuition that his struggle with Prometheus queries is a microcosm of modern warfare is actually quite profound. The civilian world develops these tools for observability and scale because we want our websites to stay up. The military adopts them because they want to win a high-intensity conflict against a peer who is also using these tools. The latency SLA for a website might be 200 milliseconds for a page load. The latency SLA for a kill chain is the difference between life and death.
The stakes are the only difference. If your Grafana dashboard fails, your SLA drops and maybe you lose some revenue. If the Maven Smart Systems pipeline fails during an operation like Epic Fury, you lose an entire carrier strike group or you miss a critical window to prevent a larger conflict. This is why the Pentagon is so obsessed with kill chain compression. They realize that in a world of hypersonic missiles and autonomous drones, the side with the lowest latency wins. Period.
So, if we're looking at practical takeaways for the folks listening who maybe aren't in the Pentagon but are dealing with high-scale data, what is the lesson here? To me, it seems like the big one is that if your architecture scales quadratically, you are building a future failure. You have to move to a common normalized event bus, or you will eventually be crushed by the weight of your own integrations.
That is the number one lesson. Standardization at the ingestion layer is the only way to avoid data silos. If you allow every team to define their own schema, without a central registry or a normalization strategy, you are just building technical debt that will eventually become an operational bottleneck. The second takeaway is that human in the loop is often just a polite way of saying high latency data cable. We need humans for the command part, the ethical and strategic decisions, but we should be removing them from the control part, the manual movement and formatting of data.
I like that distinction. Command is about why and should we, while control is about where and how fast. Let the machines handle the where so the humans can focus on the should we.
And the third takeaway is the importance of the edge. We are moving away from the idea of a centralized God view in a bunker somewhere. The real intelligence is happening at the periphery. Whether you are a soldier in the field or an IoT sensor in a factory, the closer you can do the processing to the data source, the more resilient and responsive your entire system becomes. Centralized clouds are great for batch processing, but the edge is where the real-time world lives.
It is a fascinating shift. We are moving from a world of secret bunkers to a world of distributed clusters. The nervous system of war, as we called it in episode 767, is getting a massive upgrade to its processing power and its bandwidth. It is no longer about who has the biggest gun. It is about who has the most efficient message broker.
It really is. And it is all being powered by the same technologies that run our modern web. It is Kafka. It is edge computing, it is machine learning for data cleaning, and it is robust, event-driven architectures. The fact that Palantir was able to compress those targeting systems for the US strikes just last week proves that this isn't theoretical anymore. It is the new standard for operational excellence. If you can't manage your data pipeline, you can't manage your mission.
Well, I think we have thoroughly deconstructed why Daniel's Grafana headache is actually the front line of modern geopolitics. It is all about the pipeline. Before we wrap up, I want to say thanks as always to our producer, Hilbert Flumingtop, for keeping our own data streams running smoothly.
And a big thanks to Modal for providing the GPU credits that power the generation of this show. We couldn't do these deep dives into the technical architecture of the world without that kind of compute behind us.
This has been My Weird Prompts. If you are finding these deep dives into the intersection of tech and the real world useful, we would love it if you could leave a review on your favorite podcast app. It really helps other curious minds find the show.
You can also search for My Weird Prompts on Telegram to get notified the second a new episode drops. We will be back next time with another prompt from Daniel.
Until then, keep an eye on your latency.
And your schemas. Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow takes to facts on cue. We shake